All right, so now we have started. So we talked about Faraday's law of induction. In particular, we talked about, this is where we want to start, that the electromotive force can be induced in a secondary coil, can be related to the magnetic flux through that coil from a separate source. Now, it's important to be able to label these, right? This would be the primary source of the field. This is the secondary coil. And as we look at things like Lenz's law, it's going to be extremely important that we can separate these in our minds. I'd say the most confusing part of learning about induced fields and induced currents and things like that is separating in your mind what's applied and what's secondary. All right, so whenever you're doing one of these problems, keep in mind that there's an applied field, right? That field is applied from some primary source. And you're looking at how that field, not its value, but how it changes in the secondary setup. Okay, we talked about that a little bit before, and I made a mistake in the example for those of you who are here long enough to see that. I want to clarify it here because sometimes the wording is confusing. But you know, that's okay. We learn from our mistakes. So if you remember the problem, we did this problem last time, so we're not going to do it again, but we just want to interpret it so we know what we're looking at correctly. So we will read it. So the long solenoid S is shown here in cross-section form. We have our long solenoid here. It has 220 turns per centimeter, and it carries a current of 1.5 amps, and has a diameter of 3.2 centimeters, right? So that's all the properties here. Now, at its center, we place a 130-turn closely packed coil of diameter 2.1 centimeter. The current in the solenoid is reduced to 0 at a steady rate of 25 meters or 25 milliseconds, right? What is the magnitude of the EMF that is induced in the coil while the current of the solenoid is changing? So we're able to find this, but we have to look at the flux through the coil. So essentially, to look at the equations, and again, I'm not going to go through the whole problem, but if we look, you know, this is essentially a Faraday's law problem, right? Equals d phi b over dt. And in this scenario, over delta t, and we write it like this because we already have delta t, and we want to note the EMF, right? This is what we want. So it's important that we look at the magnetic field, delta phi b, as equal to b times a in some capacity, right? But the b comes from the solenoid, right? This is the applied field. So you have this circle, you'll have the solenoid field going through the center of the solenoid. That's how we model solenoids. However, the area is the flux. You're looking at the induced EMF in the copper, so you have to look at the flux through the copper, okay? And you have to be careful there. So it's that magnetic field into the area of the surface area of the object you're looking at. So I wanted to make that clear, and going over this conceptually is a good warm-up for what we're going to talk about next, which is Lenz's law. All right? So, so Lenz's law will hopefully clarify some of this, but does this idea make sense? And I want to go back to the main idea that should make sense, which is that if you have a steady state magnetic field, you will not induce current in the secondary system. You need a changing magnetic field. That's why you cut the power, and over 25 milliseconds, you go from a current of 1.5 amps to effectively a current of 0, right? So you get your delta T. You can use your solenoid equation to find the magnetic field, right? Because you have the current and all that good stuff. And then you have to find the area from which you go through here, that your flux pierces through. Okay? And that will give you your magnetic field, or your EMF. Okay. So go to the chat, see what I missed. All right. So this brings us to Lenz's law. Now, Lenz's law, the way we've learned about Faraday's law, it'll seem like Lenz's law is the same. And a very smart man who I took this class from at the doctoral level would often make the claim that they really were pretty much the same. Where Lenz's law, where Faraday's law is a little more general, and Lenz's law is a little more specific to induced fields, right? So what I mean by that is we can expand Faraday's law to be very general, and eventually we'll relate it to electric fields. Whereas Lenz's law will just sort of stick with our EMF change. But what Lenz's law states particularly is that an induced field, so I want to highlight some stuff here as we go, an induced field or induced current has a direction such that the magnetic field due to this current, right, so this is going to be I induced. I should use my pen. Just feel like I have some more control with the mouse sometimes, right? So, so B induced, the magnetic field here, due to this current, that's going to be B induced, opposes the change, keyword here, underlined and circled, in the magnetic flux that induces the current. So the magnetic flux that induces the current here, this is going to be B primary. All right? So as the primary field is changed, the induced field opposes the change of the primary field, and that will give you the direction of the induced current. And again, if you're wondering, well, how do we figure that out? You will have to use a right-hand rule. So we can see here Lenz's law at work. And let's look here. We have a magnetic field that we're applying to a conducting ring, right? So you have to remember, if you hold this magnet still, nothing's going on in the ring. So as you thrust this magnet down into the ring, it's going to induce a field. You'll have an increasing magnetic field, and the induced magnetic field, right? So this is B primary. The induced magnetic field, so we're down and increasing, so then we want to be going up, right? So B induced will be up. And I want you to see these as two separate entities. All right? And of course, if you use your right-hand rule and you stick your thumb in the direction of the magnetic field, the way your hands curl will tell you the direction of the induced current. So if you see that the induced field is up, you'll notice that it curls with this counterclockwise rotation. Okay? So you'll notice here the current produces its own magnetic field with the magnetic dipole orientated so as to oppose the motion of the magnet. That's just what we did. And this induced current must then be counterclockwise. So again, I want you to see that we look at the magnetic flux from the primary field. It's going down and getting bigger, you know, it's increasing as this as the bar magnet goes towards the loop. So if I'm going down and getting bigger, my induced magnetic field will oppose that change. It'll want to keep things normal. So if my initial field is down and increasing, the induced field will be up. All right? And then that'll oppose the change. And it doesn't oppose the field. Now, I want you to keep in mind, it doesn't oppose the field. It opposes the change in the field. So, for instance, if you were pulling the magnet away, right, and you had B would still, you know, your applied B would still be going down, but it would be getting smaller. Then the induced B, because it's getting smaller, would actually be in the same direction as the field. All right, because it's opposing the change in the field, not the field. That is super, super important. So you'll see we have a whole list of these things that gives us each of the possible conditions here. So you'll notice that we just looked at something like this, part A. is just what we looked at. And it's hard to see, it's a bit of an optical illusion, but you'll notice they have B applied. It gets a little bigger each time. And if you're having trouble seeing this, put your hands as the size of the arrow and keep them the same size, and then move them. And you'll notice that as time goes on, B gets bigger. And if B is getting bigger down, the induced field will oppose the change. It'll be pointing up. But now you'll notice this was the situation I was talking about, right? Where B is still pointing down, but now it's getting smaller, right? You can see that clearly through each of these three rings. So if it gets smaller, the induced field opposes that change and will actually be in the direction of B, right? Because again, it wants to sort of keep things at some regular value. And then when you do that, you'll notice that your thumb now points down and you'll curl in a clockwise direction, all right? Which is what you see, oh dear, which is what you see here in B, okay? Now, the other ones, we can look here. If we have an increasing up, right, you'll notice that, again, if you're increasing up, you're inducing down. And if you're induced down, again, you'll have a clockwise rotation. And then vice versa with the B field being up and decreasing, right? And then the induced field will be in the same direction as the field, but opposite the change in the field. It's important to always see that. And so these pretty much exhausts your situation with Lenz's law. The important thing to recognize are the difference between B and B induced. All right? They're two things. B induces B induced. Once you can get that, then the next hard part to get is that B doesn't oppose the field. B induced opposes change in B primary. All right? So that change is important. That's the key. So that can get confusing, and I would ask you to ask yourself these questions. Where's my primary field? Okay, how is my primary field changing? Once you figure that out, B must oppose that change. And then once you figure out which direction B is going, then you can figure out the direction of the induced current. Okay? Questions, thoughts? Yes, Lewis. Are you talking, Lewis? I can't hear you. Okay. So the fingers, if you look at the slide up here, you'll notice the thumb signifies the direction of the induced field. And then the current, when you close your fingers around the thumb, that just tells you the direction of the induced current. All right? Thumbs up for the induced field and fingers for the current. I'm trying to think about Anthony's question about the meeting with Lenz's law. So what Lenz's law you can think of as a criterion for figuring out the properties of the induced magnetic field and current from how the applied field changes. And the real trick is understanding there's two magnetic fields here. There's the applied field. The applied field acts on a ring, like these rings here. And so what Lenz's law tells you is that if I know how the applied current is changing in a conducting ring, like one of these, then I know how the induced field behaves, because it has to oppose the change. And then from my right-hand rule, if I know which way the induced field goes, I know which way the induced current goes. And again, you can actually put a current meter and measure the current in these in a circuit like this and see that a changing magnetic field does lead to a EMF or a current, an induced current. Okay? I don't know if that makes sense, Anthony. I'm hoping that that at least gives you the function of Lenz's law, like what it does. But good. Okay. Good. And hopefully anyone else who's struggling with the same question, because I think it's a fair question, important question. It can with talking about how all the fields are moving, it's really easy to get lost. So I think it's good to sort of step back and sort of take stock of what it is in the context of what we're talking about. Okay. So I think we are in good shape there. We now want to talk about induction and energy transfer, and we really want to talk about how power can be dissipated, how you can sort of electrical power dissipated in a current carrying loop as you move it through a magnetic field. Now, this is a real classic problem in Physics 2. So we're going to go over it, and we're going to talk about it. I just want to be sure I'm not going to miss anything with what I say. Good. Okay, so this paragraph doesn't have anything extra than what I want to say. So the problem is this: is you have a current carrying wire, right? Or not a current carrying wire. You have a conductive wire, and you have a magnetic field going through it. Now, we've talked about the field itself changing, but we haven't talked much about the area changing. And I want to remind you that Faraday's law says that the induced, that squiggle is terrible. I gotta change colors and all that good stuff. Hold on, I just want to be sure I'm not going crazy. All right, yeah, I thought I was missing a minus sign. But that's okay, because what Faraday's law tells us is that, I was forgetting my magnitude symbols, is that the magnitude of the EMF is equal to the magnitude of the change in magnetic flux over dt. The minus sign gives us sort of a more Lenz law looking equation, but that's okay. What we can see here is that as this flux changes, phi is equal to BA. We've talked about B changing, but we haven't talked about A changing. And in this particular problem, it's A that will be changing the flux, the reduction in A as you move this wire through at some velocity V. Okay? So, when we look here, we have a magnetic field, right, going into the board, and a conducting loop that is being pulled with some relative motion with respect to that B field at a velocity V. Okay? And we can look here, we can look at this and look at the, if we want to look at the power dissipated and talk about the power of the system, we'll want to talk about the energy of the system, right? So that'll give us to this rate of work. So to pull the loop constantly at some velocity v, you must apply a constant force to the loop because the magnetic force of equal magnitude but opposite direction acts on the loop to oppose you. So let's understand that, right? What we know is that if we induce a current, right? If we move this bar through this magnetic field, this will induce a current in this wire and an induced field, right? That will then generate, right? Force is equal to I/L cross B, if I remember that correctly, which I'm pretty sure I do remember that correctly. So if we look at this, we'll have an induced current and an induced field. So that will create an induced force as the current goes along the wire. Now, F2 and F3 are going to cancel out, so we don't have to look at those. But you'll notice this F1 here is going to oppose, it's going to be in the direction opposite which you're pulling. So you're going to feel this pull, all right? So we can look at this power from this force mechanically. right? If you remember, power is equal to F dot V, and these are at least V is in this direction, F is in the other direction, so we might get a minus sign, but we can say that the magnitude at least is FV, right? Where F is, oh, I see, where F is the magnitude, so the power of the force you have to pull, that force will be in the same direction as V, so then this is trivial. F1 is the opposing force that you get. All right. So we have that part there. Now, to look at the induced EMF, right, we need to look at, let's write down Faraday's law again. Okay, so first we want to concentrate on our flux term, right? So that will be equal to B times A. So B is constant, so that's easy, right? But now we want to look at this A term. Well, if you look at the rectangle, right, you'll notice that wherever you are, you have this L value. L remains constant wherever you are. Some of those are better than others. And you'll notice that you can multiply it by however much of the other side is in you can multiply it by the other side by x, right? However much of this x here is in this rectangle. So in that sense, you can look here and say that the area is equal to the length times x, okay? It's a rectangle, so that shouldn't be surprising. So that gives us this expression for phi. And you'll notice when we use Faraday's law to take the time derivative of phi, of BLX, you end up with this dx dt term, which we substitute with v. All right? The speed at which the, in which this moves. So now you'll notice we have, if you recall from the last slide, we have power is equal to FV in one instance, but we'll also know that power is equal to the current times squiggle here too, right? At least the power dissipated. So as we go forward, we can solve for the current. Remember, squiggle equals IR of this type of problem. And so we have again, in order to to get the direction of the induced current, we just remember, right, we're decreasing into the board. So that means our induced field will also be into the board. And so we get the direction of the current pretty easily. But then we also have the magnitude can be solved for in a pretty straightforward manner. And we have this expression for the current. All right, and we can see in the circuit, we can sort of see how this all goes. And again, we pointed out that those up and down F2 and F3 forces will cancel, and that the force that you pull with will have to be equal and opposite to F1, right? That'll be an opposing force, which will oppose how much you pull. And we can see that, hold on, my whole computer's being obnoxious. All right, so we can see that that's the stuff that's just stated here. And again, we're using our force here. Remember, this is just coming from F equals I L cross B. So this is where this term comes from. And the applied force will be equal to the opposite, F1. Oh, I didn't even see that they did that here. You can see it twice. So again, when we look at this here, we can, let me see, what was the last one? We can use our expression for I, for the force, right? We have that current. We can plug that into our force equation, and we now get the force, right? And once we have the force, we can multiply it by V, like we did before, and we have this expression for the power. All right, now note that the work that you do in pulling the loop through the magnetic field appears as thermal energy in the loop. Okay, so that's sort of, so let's go back. We've seen it once. Let's go back and summarize each part of it and see how we constructed. Now that we see where it's going, let's look at it again. So the question, the fundamental question is, how much power is dissipated, you know, electrical power can you get from moving this loop through this magnetic field? All right, and I think you have a few, I picked out a few homework problems based on this one too. So you'll notice that you're pulling the force, right? This isn't labeled here, but that's fine. You're pulling the force, and you can, that's F applied. And you can see here that as you pull, you will be decreasing, right? The fraction of the rectangle that's in this magnetic field gets smaller. So if you want to understand, you don't need them to draw the induced current, but you can see where it is. Put your thumb where the current is, which will be going into the screen, right? And it's decreasing. So if it's decreasing, that means you'll want the induced field to point in the direction. The V induced will also point into the screen to add to that decrease, right? To oppose the change. So in that sense, your fingers will tell you the direction of the induced current. And we can see from our definitions of power that with power being the rate of that work is done, we can see here that P equals FV. And what's more important is we can see that F equals IL cross B. So the question is, how do we find I? How do we find the induced current in this loop? And we ask that question because what you can see here is that the induced current leads to the force, right? And then once we have the force, we can get the power. Okay? And that's just what we do as we go through this loop. First thing we do is we need to use that flux to find the EMF. That's this step here. So we have our flux. We just look at the geometry, and we can get a nice expression for the EMF, right? And then we use Ohm's law. Right, because there will be some resistance in the wire. That's fine. And we can use Ohm's law to get an expression for the current. And then, like I said, once we have the current, we can get the force. All right, and then once you have the force, you can figure out the power. And you'll notice that the power is in terms of the resistance, right? The resistance of the loop, the speed at which you're pulling, the length, and the magnetic field. Okay? And that will give you your power dissipated. Now, during this lecture, I usually have a demo. So during break, which we're not really at yet, but during the break, I'm going to ask you to look up eddy currents. So be sure to do that in case I stop recording or something happens between now and break. I usually keep it recording during break. But you're going to want to look at videos of eddy currents, and you can actually see some of this stuff in action, and it'll make a little more sense. It'll also look like magic, which makes it pretty cool. But you'll be able to see it all in action. All right, now we want to get to said eddy currents, and we'll talk about induced electric fields. Okay? So, man. All right. Okay. So remember how I told you a while ago that we were going to get to a point where we would have electromotive forces but we wouldn't have potential differences. Well, that day is today. All right, so you can look here at in a copper ring, and let's look at it. Let's look at all these. It's a busy slide, but we're going to want to, you know, I don't like to read much, but we'll look here. So what we're seeing here is that that there's a magnetic field increase at a steady rate. Okay, if the magnetic field just keeps going up, then a constant induced current will appear, as shown in the copper ring of radius r. Right, so that's A, and you'll notice you have a current flowing around the ring. All right, and you'll notice that current, because of Faraday's law, which I want to draw up here in the corner again. Right, remember that right? So we have a flux, magnetic flux, a change with time, and we set up this current circulating here. All right. So now, if there's a current flowing, you'll remember when we looked at circuits, we were able to relate and sort of see the current as a flow of charged particles. And if these flow of charged particles exist, then there's an electric field propagating. So you'll notice, though, that at each point, if you look at the electric field, it's circular, it's circulating, a circulating field, and it always changes direction. All right? Now, this is just one small area here. If you look here at the electric field, you'll have concentric lines. And what I want you to notice is that when you try and use Gauss's law, all right, you know, when you're in here, Gauss's law, you'll notice that each field line enters and exits. So there is an electric field, but there's what we're going to find is there's no potential difference. All right. So you might want to read. So D is very busy, right? So for similar, four similar closed paths that enclose identical areas, equal EMFs induced around paths 1 and 2. So we have paths 1 and paths 2, which lie entirely within the region of changing magnetic field. A similar EMF is induced around path 3, which we have here. No net EMF is induced around path 4, which lies outside the magnetic field. Right? So you have EMF induced if your path is in the magnetic field. So what we can do here is we can look at the electromotive force, and we can write, and this is a little different than what we talked about in chapter 24, but we have that the EMF is equal to the closed loop path integral around E dot ds. All right, so you'll notice these are your paths. You know, path 1, path 2, and path 3. So path 1 and path 2 have the same amount of magnetic field flux going through them. They're entirely within the conductor. So if you were ranking them, you would say that E1 equals E2, which is greater than E3, which is greater than squiggle 4. Okay? But again, these are these eddy currents. You'll notice if you have a potential difference, and I think it's going to make that point in a minute, there's no potential difference anywhere along this path, right? The EMF is always the same according to our induced EMF, our expression for EMF here, right? The only way you can get a change in it is to not have as much magnetic field in there, because you're decreasing the rate of magnetic field change, right? Like you have here in 3. So we can generalize Faraday's law, and this is generally why it's looked at and considered different than Lenz's law. So the first thing we saw, where we just have the, in a more advanced class, you'd be introduced to Faraday's law this way, and then you would write Lenz's law as the EMF is equal to minus d phi b dt. That would be Lenz's law. All right? So we called Lenz's law Faraday's law and then, got into it. But you'll notice here electric potential has meaning only for fields that are produced by static charges. This has no meaning for electric fields that are produced by induction. So what we find here is that we actually have two sources for EMF, two physically different sources. An EMF can be created by static charges and creating a potential difference, or it can be created by a dynamic magnetic field. Right? Those are our two sources for EMFs, for electromotive forces. And it's the reason why we can't just say, oh, squiggle is V. This is only true for potential differences. There is no potential difference here, but there is an EMF. Creepy, huh? And Faraday's law in this form brings us to almost the completion of the Maxwell equations. All right, so we have Faraday's law, Ampere's law, and Gauss's two laws. So we're almost there, but we're not quite there yet. And you'll see what I mean. We're going to have to build up the one component that's missing to collect those four equations together and call them Maxwell's equations. So we still have to build up that last piece of the puzzle. Okay, any questions on this? No? Okay. So we're going to now look at how to incorporate in the effects of induction into our circuits. All right. So that will bring us to inductors and inductance. Now here it becomes a little easier, but you want to notice a few things. All right. So inductors are usually looked at as coils. So we can look at, in a circuit diagram, they'll usually look like some sort of spring, like that. Okay. And the inductance L of an inductor is determined on how many turns you have in your inductor, the magnetic flux, and then divided by the current. However, you should note something here. This is sort of misleading in that it seems like the inductance it depends on the current, which by definition it is, but so is the magnetic field, right? So generally, when you look at this, this will be equal to N BA over I, right? Now B will usually depend on I in such a way that this will get canceled out. And so, for instance, if you look at the inductance per unit length near the middle of a long solenoid across with some cross-sectional area A and N turns per unit length, you'll recall that the magnetic field of a solenoid, right, B equals mu naught Ni, right? And so that's count per length. So when we look at this, we want to find the inductor of the same solenoid. We have to look at B equals, or sorry, we can look at this as L will equal N. Phi B is going to be equal to B times A, right? And then we want to say that that's going to be over I. So you'll notice here the I's cancel, right? Now, if you recall, equals N, right? So N is turns per length. Now, if we plug this here in here, we can say that N, big N, is equal to N times L, or I have to use a different L, right? Because our big L is now inductance. So I can do that, and I can solve for inductance over length is equal to mu N squared A. That's where you get that from. So what I wanted to point out here is that even though our definition of inductance depends on I, usually when we imply the magnetic field, that I is going to come out and cancel the current. All right? And the SI unit for inductance is a Henry, given in H, and it's equal to, a Henry is a Tesla times a meter squared over amperes. All right? So, I don't know what that is, but I think I heard a car alarm in the distance. Okay, that's what I was talking about. So, when we look here, if we consider a case in which we have two coils, which we can now call inductors, right, are near each other, the current in one coil will produce a magnetic flux through the second coil. Okay? We have seen that if we change this flux by changing the current, an induced EMF appears in the second coil, according to Faraday's law. So now an induced EMF appears in the first coil as well. So this is now a self-induction process. Okay? So basically, let's look here. Let's see because I want to draw the whole picture. So let's be sure we have it all. An induced EMF appears in the first coil as well. This process is called self-induction, and the EMF appears as, oh Lord, it is called a self-induced EMF. It obeys Faraday's law of induction just as the other induced EMFs do. For any inductor, N phi B will equal L times the current, and Faraday's law tells us that the EMF through the inductor is equal to minus dN phi B over dt, and by combining those equations we get this simple equation. But now let's look at this, right? So it's saying we have two coils, because this will sort of be, so the coil, that's coil 1, and now we have coil 2. All right? So when we look here, coil 1 is going to create, actually I want to do a different color. So we've got coil 1 will have a magnetic field, right? So that magnetic field will cause an induced field in coil 2, right? This will be B induced. And then that B induced will cause a self-induction in coil 3. Self-induction. All right? And so an induced EMF appears in any coil in which the current is changing. So basically, if there's current changing in this coil at all, and essentially what would happen is the induced field would have lead to a change in the current here, that would be a self-induction, because it all starts with this primary coil. All right? It can seem like turtles all the way down, but we're going to see with mutual induction that things sort of mutually inducing each other, and that's about it. All right. So I just want to be sure I didn't miss anything here, because usually when I do this, I just think of Lenz's law and like I'm done. Because this to me is the same thing. It's just another step to it. Okay. All right. And now we get into the fun stuff. We get into circuits. So when we look at an RL, so the first circuit we're going to look at is an RL circuit. Well, much like I say that in the first circuit, like we never looked at anything before. So much like when we had a capacitor, and we looked at the capacitor circuits, we were able to combine the capacitor with the resistor by itself, and interesting things happened, right? We were able to come up with a differential equation. And now you'll notice we sort of are in the same boat here with the oh geez, my pen, with the resistance and the inductance, right? With the current going down. Now, you'll notice that you have your EMF battery, but you'll also have EMFs due to the Faraday's law, right? You'll notice they kind of point in opposite directions. So when we do this, when we do the loop law, we'll start at one point, we'll move around the circuit, right? So we'll have epsilon naught, this IR, and then this is going to be, I don't want to mess up the sign, I believe it's going to be minus L di dt. And that's going to equal 0. Okay? Now you can check this to see if I got the sign right by plugging in the solution and seeing if that's what you get. All right? Because remember, when we develop these ordinary differential equations, that's sort of at the level we're at where we can plug in and solve this equation for I. All right? And you should get this function, which is that I equals squiggle over R times 1 minus e to the minus t over TL, where the inductive time constant is the inductance over the resistance. Now, that being said, you can intuit the behavior of such a circuit by looking at the extremums of time, right? So we can see that if time goes for a very long time, right? So if t, well, first let's look at t equals 0. So at t equals 0, this will equal 1. You'll have 0 current, right? So as time goes on, we go from sort of 0 current to looking like a constant wire, right? So in a long enough time, the inductor looks like a long straight wire. This is sort of opposite the capacitor, right? If we remove the EMF, we can get a decay in current and have something somewhat similar, and we can go from acting like a long straight wire to a break in the circuit, right? So at first, you can see that here. At first, at t equals 0, I is just equal to e over epsilon over r. I'm realizing I don't have my cursor on. Is equal to squiggle over r, right? But then as time goes on, the current decays and goes to 0, and it looks like you have a break in the circuit. All right, so you'll notice you have both graphs here that give you the behavior of voltage versus time. So we've sort of seen that these situations, these decays, these growths and decays for voltage and current with direct current batteries. But the next thing we're going to talk about, our very next chapter really, will be building up, well, what happens if we have time varying voltages as well? All right, and that will introduce us to alternating current. But studying alternating current in and of itself is interesting, but it relates very directly to some very important features in physics that will help us finally construct our Maxwell's equations. All right, and so we'll look at that and look into that. Okay, so if we look here, we have much like we used looked at capacitors and the manner in which they stored the electric field. We're going to see that inductors store magnetic energy. All right, and you can look here at the for an inductor that carries some current through it. The inductor's magnetic field stores an energy given by UB equals 1/2 Li squared, where again L is that inductance. And so let's just go through a simple example, right? So we have a coil that's given some 53 millihenries of inductance and a resistance of 35 ohms. So the question is if a 12-volt EMF is applied across the coil, right? So across this coil, that's 12 volts. How much energy is stored in the magnetic field after the current has built up to its equilibrium value? So we know that we're building up here, right? So we know from our last slide that as t approaches infinity, the inductor acts like a wire. So that's going to allow us to just plug in Ohm's law, and we can use our voltage and our resistance, and we can get the current. But that's not what it really asks for. It wants to know the magnetic, how much energy is stored in the magnetic field. But that current will be important, right? So now we have the we've got the value of the current. 34 amps is a lot, and we have L, and we have 1/2. So it seems like substitution will give us 31 joules. It's that straightforward. All right, that's how much energy is stored in the magnetic field there. So now it asks us an interesting question. After how many constants will half this equilibrium energy be stored in the magnetic field? So these are interesting questions because it's asking at what time will the energy be equal to 1/2 of the maximum energy, right? 1/2 UB infinity. So we can write that here, and you'll notice that you have here I on one side of the equation, you have I and I infinity. It's a little small. All right. So you can look at here, you want to look at the current, the time it takes when the current is equal to 1 over the square root of 2 I infinity. That you just get from playing around here. Okay. So then you can plug right back into the equation your desired value of 1/2, or of when the energy is 1/2, right? You'll notice the current isn't 1/2. It doesn't scale. It's, the energy is divided by 2. So then that current will be 1 over square root of 2 I naught, or I infinity. And then so you have your final value, but then you set it equal to your function of current as a function of time, and then you just solve for t, right? That's all you can do. And you'd have to take a natural logarithm there, and you get your t over L constant is equal to 1.23. So t would have to be equal 1.2 times the time constant. So what I want you to see is that this stuff is sort of like a puzzle, at least when we start getting the circuits. There's going to be a ton of terms and a lot of elements. There's a lot to do, but a lot of it is really just being able to look at the puzzle pieces and put it together, right? It's like being nibbled to death by cats. So let's take a break. So it's 6:52. Let's come back at around 7:05. And we will continue. We will wrap up this chapter, and we will start looking at alternating current circuits. Okay? So I'm going to be smart this time and load the file. And I will be on break. Okay, everybody, we are back. All right. So I just did a little bit of looking, and it turns out we're not as far behind as I thought. So maybe we'll just take that Memorial Day break. I don't know. I'll decide as we get closer to the end of May. We'll see how we do. Anyhow, we want to move on to energy density in a magnetic field. So remember, if you look here, much like with capacitors, we're able to look at the energy stored in the magnetic field through the inductance, right? But much like we needed for the energy density for to relate the energy stored directly to an electric field, we'll have to do a similar calculation when you'll notice that's what AL is down here, right? It's area times length, so that's energy per volume. We need something different, and when we apply that here, we can get for the solenoid, you'll notice you get basically a b squared, and you just move the mu naught down here, and then you get the full b squared is equal to the energy density. And what this allows us to do is relate energy in a sense to the field directly. And what we can see here, and the big takeaway is that electric fields and magnetic fields can store energy, and because they can store energy, they can transfer energy. All right, and that's a very big deal, because as we all know, sort of taking a step back into what physics is really all about, it's about how energy, one of the things we see in whether it's quantum physics or general relativity is, or classical mechanics or E&M, whatever we're looking at, is the energy of a system and how energy transfers within a system, and then using the energy of a system to get the dynamics and behavior of a system. All right, so this gets us back to that sort of core structure of the subject. The last thing we want to talk about is a bit of an advanced topic, mutual induction. We already sort of saw this with the a little bit with self-induction, but basically you get two. If you look at two systems, right, and you change them to which one has the R, you can see that they'll mutually induce. They'll have different EMFs, but they'll have the same mutual inductance quantity M here. All right, so this is a inductive quantity, and proving that the M12 is equal to M21 is a little beyond the scope of the course, but that's essentially what we see with mutual induction here. And we're not going to spend a lot of time on that. We are going to move on to our next chapter. So let's stop sharing this and let's go on to chapter 31. Okay. So we're going to first start talking about electromagnetic oscillations, all right? And I want to kind of go slowly through it so that hopefully it makes as much sense as possible. So after we get through all the learning objectives, we have we're sort of carrying on with our conversation from our last class, from just a few seconds ago, right, where we talked about the energy of a magnetic field stored in the magnetic field and the energy stored in the electric field. Now, pick another color. So we have UE and UB. All right. Now you'll notice that for the electric field, we had capacitors, and we'll start here with a completely electric circuit. You'll notice we don't have a battery here, but we have a capacitor connected to an inductor. All right. And so we start off with our energy all being electric. Well, this is just a snapshot in time, right? Once we're fully charged, the capacitor will want to discharge, and that's going to create a current. As the capacitor discharges, it'll create an increasing current going this way around. Remember, the current is always even though the charge carriers are negative, the negatives will want to flow through the circuit this way, and the current will be in the opposite direction. All right, so you'll recall that's our convention. But as the current goes through the inductor, that change in current, right? There'll be a change in current here that will induce a magnetic field. All right, and then as we and you'll notice that our energy, our total energy, has to remain the same, right? So if we had, remember, you'll recall from conservation of energy, UE plus UB has to equal U total. UB and UE can change, U total can't. So if it's 5 joules, it'll be 5 total. When you add the two bars up, you have to get the same 5 every single step of the way. Okay? But there's a lot going on here. It's not just about energy conservation, but you'll notice that the current, the capacitor discharges, right, until we get to our inductor. All right, so now our inductor is has fully stored that energy in the magnetic field, and we have the current still going, right? But it's now going to change and slow down a little bit, and so we'll notice that the magnetic field is going to decrease as well, but now that current is going to pile up the positive charges on this plate and the negative charges on the opposite plate, and that'll take us to, it'll make us look like we got to the same thing, right? But we really haven't gotten to the same way, because even though all of our energy is capacitive, or in the capacitor it's electric, you'll notice that the current sort of kept traveling one way, and we've gone from a charged capacitor to a charged capacitor, but the plates are inverted. In order to truly finish one cycle, not only must all the energy be electrical, but the charge distribution must be the same. Charge distribution is not the same. However, you'll notice that as the capacitor discharges this time, it will do so with the current in the opposite direction, right? So the current will now go clockwise around the circuit. And then again, as that current changes, that you'll lose energy in the capacitor, and that will transfer to the inductor, right? And then after that long time, the current will still flow, and that you'll notice the field directions have been reversed as we go through. You can use our convention for electrostatic fields and Lenz's law for the opposing current in the inductor. And so as we have that go around, we eventually discharge the capacitor and have the inductor, but now the current will start to decrease through the inductor, which will start charge building up on the capacitor, and you'll notice that we have split energy levels, and that gets us back here to where we started. And so not only can we store energy in our electric field and our magnetic field, but by creating this LC circuit, we can create an electromagnetic oscillator. All right? So that's pretty cool. And oscillators, the analysis of oscillators, whether they're mechanical or electromagnetic or quantum, are pretty fundamental in the study of physics. So being able to build an oscillator is a pretty big deal. Okay, if you want to read the busy paragraph, you can, but we pretty much covered everything in there. So are there any questions on that? Take a look at that and see if there's, if anything's coming up. What you'll see in our, finally, my mouse has been charged. What you will see is that we can see each energy part, right, with the capacitor for the electric field and the inductor for the magnetic field. Okay? Okay. Now, again, I already alluded to the fact that the oscillators that you look at, that you see here, are similar to mechanical oscillators and quantum oscillators. And while we're not really ready to cover quantum oscillators yet, you can see that they make a comparison between the block spring system you learned about in Physics 1 and the LC oscillator we just talked about, all right? You'll notice that Q corresponds to X, I corresponds to V, L to M, and 1 over the capacitance to the spring constant K. All right? So the correspondences that are listed here suggest that to find the angular frequency of oscillation for an ideal, that is, resistanceless LC circuit, K should be replaced by 1 over C and M by L, yielding this frequency. All right? So let's take a look at that. You can see what they're doing. They're sort of solving by analogy. So if you remember, omega equals square root of M over K. So if we just plug in the corresponding things here, oh, no, I think it's K over M. Yeah, K over M. Okay, that looks better. So now we have, so if we plug in, if K is equal to 1 over C, right? So I'll do this in the 1/2. So that'll give us 1 over C. And then M is in the denominator. So we have L. You'll notice that this indicates that our angular frequency of our oscillator is just what they write here, the square root of 1 over LC. And this will be, we'll find that this will be important because much like a cavity, if you have a capacitor, a given capacitor and inductor, like a mechanical cavity, you can resonate if you drive a driven frequency at the resonance frequency, you get a resonance mechanical system, which may explode. You can do the same thing with electromagnetic oscillators, right? Where the resonance of the circuit will be given by this omega, this angular frequency equation. And then the question is, what are you driving at? When you have a driven oscillator, can you drive your driven frequency equal to that omega frequency? And what interesting things happen there? And that's one of the things we'll be talking about. So now this is kind of fun because this is how you essentially how you set up equations in advanced physics. So this is kind of taking the training wheels off. So in order to look at and analyze and come up with an equation of motion for the LC oscillator, you'll notice we look at the total energy present at any instant in an oscillating circuit. It's just the sum of the two energies, right? So it's UB plus UE. We saw that in the previous circuit or previous slide. And then you can just replace that with Li over Li squared plus Q squared over 2C. Now, you can invoke the conservation of energy, right? And say that for the total energy, du dt will be equal to 0. And then you can get a conservation term that will help you make sense. So let's take a look at that. Let's take a look at that here. So when you have this du dt, we know right away this equals 0 because that's just energy conservation, right? It's a system without friction or losses. But then let's take a look at our derivative term here. I'm gonna go term by term here. So if we look at this here, Q squared over 2C. All right. So if we look at this here, you'll notice that we can rewrite this equation, and we can separate each of the square terms. So you'll notice you have an Li, and then you apply the derivative to a single term here, and they do the same thing here, right? To dq dt. Now, when you look at this, when you look at this equation, let's see what it becomes. You have Li di dt plus qc over c times dq dt. But I want to point out something to you. One, this all equals 0, and two, this dq dt, remember dq dt is equal to I, right? So that means that this I cancels with this I, and we essentially have L yeah, I didn't mess that up, did I? Yeah, di dt is going to be equal to the second derivative of q. That's right. I'm not crazy. Plus q over, or 1 over c times q equals 0. And if you take when you take differential equations, you'll see that this is a second order homogeneous differential equation, and this is also the differential equation for a harmonic oscillator. All right, so this allows us to solve this equation and get, you know, something of the, you know, you want a function whose derivative, second derivative, is equal to itself. So if you get something like, if you look at this and you try q equals sine theta, you'll notice that that will, you know, you'll have to be a little more crafty, but basically q is proportional to sine theta. You'll see that that satisfies the equation, and cosine theta will also satisfy the equation in a sense too. All right. So looking at that, we're going to look at the solution. Q equals q cosine omega t plus phi. So you're going to notice that we're starting to look again like the beginning of the semester. You see why we keep waves till physics 2. So the solution of the differential equation that describes the oscillations in these resistanceless circuits is given here. I very much recommend that you find the second derivative here, plug it back into the equation, and get your verify that the equation makes sense. Now, you'll notice that I is equal to dq dt. You just take the derivative of the function q, and using the chain rule and the fact that the derivative of cosine is negative sine, you will indeed get this function. All right, so that's just some simple calculus right there for you. And we have our expressions for q and current in these oscillatory signals. So let's do a quick example to see if we get the you know, the gist of conceptually what's going on here. So a capacitor in an LC oscillator circuit has a maximum potential difference of 17 volts and a maximum energy of 160 microjoules. When the capacitor has a potential difference of 5 volts and an energy of 10 microjoules, what are A, the EMF across the inductor, and B, the energy stored in the magnetic field? This can be done by inspection. So all you have to do is recall what I often say is the most important rule in physics. All right, so I'll give you a minute or two to do that. Hmm. Anyone come up with anything? Is anybody out there, out there, out there, out there? Okay. Well, let's take a look at it. What is the overarching principle we've been discussing today? And believe me, I know I'm kind of tired too. So the overall thing we've been talking about, let's go back and look at it, because we're even ahead of where I want to be today, is we're talking about fundamentally in an LC oscillation, we're talking about the energy transfer between a electric field with energy stored in an electric field in a capacitor and energy stored in a magnetic field in an inductor. All right, and we have these two terms for the energy, which we'll make more use of later. Now, we talked about how using the rules we've discussed of Lenz's law and our conventions for electrostatics, we can see how the current will go one way and then go the other way, right? And that will give us our oscillating function. Now, even though all we need to solve the problem is recognize that in this particular setup that we're looking at, the total energy, if you remember what I said, has to be conserved as we go through each term here. Okay, so we can transfer our energy. Our total energy can again neither be created nor destroyed, but it can be transferred. And in this case, we're specifically looking at transfers from the magnetic field to the electric field, and vice versa. All right. Now, after I said all that, we went over some properties. We talked about the resonance condition and angular frequency of a LC circuit and came up with an expression based on the corresponding block spring system to the LC oscillator. But we also were able to find, using that fact that energy is conserved, we were able to come up with an equation of motion. Now, the equation of motion is complicated. It's the second order differential equation, right? But that's not what's needed to solve the checkpoint. What's needed to solve the checkpoint is the reasons why we can draw this equation like this. All right, and we can draw this equation, or we can draw this equation. We can write this equation. Apparently, I guess I'm a little lost too. We can write this equation because the energy is conserved and there's no losses in the system. All right, so if the energy is conserved, du dt has to equal to 0. So when we look at the checkpoint here, we want to keep in mind that du dt is equal to 0, right? And these are just solutions to the differential equation. That's all you got right there. And really, I is derivative from q. You just take the time derivative and you're done. But let's get back to the checkpoint. So the maximum energy we can see here, U max, is equal to 160 microjoules. All right, so let's just do let's do part B first. Right, good. So if that's 160, and we see that when the capacitor is a potential of 5 volts, it has an energy of 10 microjoules. So that means that the energy stored in the magnetic field has to be equal to UB has to be equal to 150 microjoules. And that's because mu B plus UE must always in this problem equal 160 microjoules, right? The max doesn't change. The individual numbers do. But under the same rules, right? If there's a 5-volt drop across the potential difference across the capacitor, and there's a 17-volt maximum difference across any given element, we know from Kirchhoff's laws that the potential difference around a closed loop has to equal 0. And so if we start a loop and we start off with, say, 17 minus 5 minus x has to equal 0, well, we can say that x equals 17 minus 5 or x equals 12 volts, which we can see are wondrous answers. All right, so does that make sense? Are we a little less lost? We don't have to be completely unlost, but just a little less lost. That's what I'm shooting for. All right. I don't know whether to take the silence as you're not lost or lost, but we can sally forth. Now, well, there's not more to it. And Douglas, if you're very lost, I hope you'll ask a question or something, because we're Anna. So Douglas and Anna, I'd say let's. What could I clarify? That's my question to you. And Anthony, what can we clarify? If we're saying all of it, it has a certain structure to it, right? So I mean, so at least in this chapter, are you with me with the? No, it's not okay, Douglas. I'm not in a rush. I mean, I'd rather spend the rest of the time getting you unlost than moving forward, because we're making good pace. So what can I clarify? If it's the whole thing, if you're thinking it's the whole thing and you just don't want to say that, that's okay. But I mean, I'll try and summarize a little bit. Well, there's a lot of confusing stuff from the last chapters into this chapter too, right? With the last chapter, really we want to understand that difference, and I'd say go back to the video and really look at the video between induced quantities versus the primary quantities and how Lenz's law work. So I'm going to say you should read the book and practice some examples and problems, some of the easy problems, the 1-star problems. That's a good way to do it. The more you actually do it, the more it'll make sense. It's not going to make. I mean, it's not going to make more sense. I don't think me explaining again will make more sense than you doing it, because then when you do it, you get lost on something specific. I can guide you through that part of it, right? So, or you can go back and say, okay, here's where I am, and there's where we go through. And and I'll tell you this, there should be enough there, if I'm remembering, how we structured induced current and Lenz's law, to, if you're stuck at any step, to sort of say, okay, here's where I am, and I get it or I don't. And we can talk about where the sources of that stuff comes from. But if we're just talking about this chapter, when we talked about inductors, is it the inductance part that's bothering everybody? Because we all get capacitors. We've gotten those for a while, right? And the inductor can store magnetic field, or it grows magnetic field, which you're seeing here, because of the change in current from the discharge and charging of the capacitor. So the capacitor discharges one way, and then it discharges, and then it charges the opposite way, then it discharges, then it charges the opposite way, then it discharges. It goes back and forth. All right? It's like a circle. All right? I'm looking at Anna and Anthony. Which problem? The checkpoint? Okay, sure. Good. All right. So fundamentally, let's look at the question and let's kind of look at each part of it. So we have a capacitor in an LC oscillator, right? And that's what we've been talking about all along, because these oscillators that transfer from electric field to magnetic field and over again. So we see here that the LC oscillator has a maximum potential difference of 17 volts. So that means our squiggle max equals 17 volts. And our U total, because our U max is equal to 160 microjoules. All right, now let's draw the oscillator so we can see. So let's draw that circuit. So the circuit has a capacitor and an inductor. Okay, that's it. No battery, nothing else. Just the ability for charge to go through the inductor and then discharge and then build up back in the capacitor again and then go back and forth. So I realize you can't see that. And to go back and forth. Now, let's take a look here. So we know, right, if we just look at, say, V equals, this is when my memory fails me. Is it Q over C or Q over C? Well, we know the voltage can be related to the capacitance, right? So we know that, for instance, the voltage is 0 when there's no charge. So it's going to be Q. I think it's Q over C. And then someone correct me if I'm wrong there. And then, but the point is we're, don't get lost here where I'm getting. This is just semantics at this point, because the point is that if the capacitor is charged, there's no voltage across it, right? All the voltage will be across the inductor. And if the capacitor is fully charged, this is the important point, all the voltage will be across the capacitor. So the maximum EMF, if you will, for any of these two elements is going to be 17 volts. All right? But as we saw, so are you with me there? Are we good so far? Okay, good. Anthony? Good. Okay, so now we're looking at some intermediate time, right? So now we're saying, okay, the capacitor, so at some time t, right? The EMF across the capacitor is equal to 5 volts, and the energy of the capacitor is equal to 10 microjoules. All right? So now if we do A, we can just use our loop rule, right? If this is 5, we have to have the, if this is 5 volts, we have to have V total has to equal V capacitor plus V inductor, right? So if this is 5 and this is 17, we can just solve for VL has to equal 12 volts. All right? So you're with me there? Good. And that's part A. I like part B as a question better because it's more subtle and important. But part B is, what is the energy stored in the magnetic field? But again, we use the same thing, right? UT, the total energy, is equal to the energy stored in the capacitor plus the energy stored in the inductor. right? So if the total energy is 160 and the energy stored in the capacitor is 10 microjoules, they're all in microjoules, all you have to do is solve for UL equals 160 minus 10 equals 150 microjoules. Okay? Does that make sense? All right. It's one of those systems where the math is actually quite simple. It's understanding the physics that allows you to set up the simple math. And if you've had me, those of you who have had me for a year now, that's the goal. That's the skill, right? That's what we keep trying to work on, is interpreting these sort of weird, wordy problems to come up with simple equations based on simple overarching principles that allow us to make predictions or discover something about a system. So I think that is a good place to stop for today. And I say that because I want you to tomorrow, if you're struggling, watch some of the magnetic field stuff and try working on some simple, not complex, not homework level stuff, but like 1-star problems, and see if practicing will help you. If you're really confused, will help you work through some of the examples, work through some of your confusion, and hopefully it'll make some sense. So at least that's my hope for you all. And this is actually a better place to stop than where I was going to stop. And believe it or not, I was only planning on going to, we're on slide 8. I was going to do a hard stop at slide 13 one way or the other. And slide 13 is actually a better place to start than to stop, to tell you the truth, getting to damped oscillations. So let's call it an evening. I'm going to take the attendance by taking a picture, but I will, of course, be around if you have any questions. Right, attendance has been taken. And yeah, if you have questions, that's great. Otherwise, you're free to leave. You're free to go. I'll just be hanging out here till about 8. All right, you're welcome. And if I don't see you, I'll see you on Thursday.
Hi, Professor Tolan.
Yeah.
For the first week of the lab that we are working on,
Yeah.
I set the resistor and the battery, and I took data for the current and the voltage.
Okay. Simultaneously?
No, I try one first and then the second.
Okay, good. But in order to do the experiment, you'll need to be able to record both at the same time.
I have to do both at the same time.
Yeah.
Okay, so let's say I do both at the same time. I only have to take data for resistor 1 and 2.
Take as much data. It's up to you. Take as much data as you think will make your case. I would recommend taking more than one data set personally. But you're designing. I gave you the circuit guide. It's up to you to design and decide when enough data is enough.
Yeah, I use two resistors because that's what it says on the sheet.
Well, so on the sheet you will use two resistors when you're doing series in parallel. So there's several experiments, Douglas. The first one should only have one resistor.
Well, I was talking about the first week, yeah, when we use only one resistor and we
But
use
why did you
first,
use two? The sheet didn't tell you to use two.
yeah, the sheet says that we need at least two resistors.
It says to do it twice for two different resistors, but each circuit should only have one resistor in it.
Yeah, so that's what I did. Like you just said, I use the
So you did it
circuit.
twice. You didn't use it two resistors in the circuit.
Oh no, no, of course not. I did it
Okay.
twice, right? With
All right. So
different,
you did it twice. Good.
and so for each time, I should have taken the data of the current and the voltage
Right.
simultaneously.
Hmm.
So that would be only two sets of number, nothing else.
Yeah. That's what you need. That's what I asked you to make.
Okay, yeah, that was it.
Good.
Thank you.
I don't have any problem with you showing the need for the use of quad precision, but I would prefer you did not share any results that used quad precision. with a chirp factor.